Hello to all electronics and tech enthusiasts, especially those of you who love cracking open devices and uncovering their secrets. Just a couple of centuries ago, no one could imagine that a teeny thing like a charger would become so crucial in our lives. But today, without the charger, our phones, laptops, headphones, even our bikes, they all grind to a halt. So, when exactly did this little lifesaver enter our lives? The truth is, the charger is a modern invention, a child of the age of electricity and electronics. In today's video, we are taking a quick dive into a history of chargers from lead acid batteries to today's GaN and wireless chargers. And then we'll do a detailed engineering focused breakdown of a real charging. I mean Samsung EP-TA60EBE model charger. What's in this video? First, we'll explain what this charger is designed for and its specifications. Then we'll dive into its internal components, examining them one by one. Metal pins and connection pads, information on the board as you can see here, key components like Fusible, resistor right here, capacitors, inductor, transformer, resistor, diode, IC, B1 and bridge rectifier. Finally, we'll take a look at the soldering circuit traces and slots on the board. And of course, we won't skip the input connector, cable, and USB port. In this video, we'll uncover how this circuit takes mains electricity and produces a precise, stable 5-volt current, delivering it safely to our phones or devices. And at the end, we'll wrap it up with a quick summary to understand what's really going on inside these teeny devices. So, let's embark on a short journey through time and see how the charger's story began. At the first, the birth of the charger, 19th, 20th to 1930s. During this era, rechargeable lead-acid batteries were first used in cars and radios. As a result, early chargers were designed solely for charging large batteries. They were heavy, lacked automatic safety features, and were only suitable for engineers and technicals. The second, the rise of household chargers, 1960s to 1980s. With the advent of electronics like Walkmans, cameras, and calculators, the need for smaller portable chargers grew. This era relied on large transformers and diode rectifiers. Chargers were heavy, got hot, and weren't smart. The third one is the mobile revolution, 1990s to 2000s. With the rise of mobile phones, chargers became smaller and more spacious. This was when USB wall chargers started taking shape. But back then, every phone had its own specific charger. Remember how Nokia charger wouldn't work with a Sony. And lastly, we have smart and fast chargers, 2007 to today. With the launch of smartphones, chargers got smarter. Fast charging with technologies like quick charge, USB-C, GaN chargers that are both small and powerful, and even wireless chargers. What exactly is this charger and what its purpose? It's a low power travel adapter, a type of switching power supply that converts alternating current, AC, to direct current, DC. Let's take a look at what the specification and the charger's body tell us. Right here. Yes, as you can see. At the first, we have Samsung, the brand name. Travel adapter indicates it's a travel adapter written in both English and Russian and means a power adapter in Russian. Right here, EP underline TA60EBE, the charger's model number. Then we have a input. So, input voltage range 100 and 240 volt compatible with most global power sources. Then we have a frequency, 50 to 60 Hz standard AC frequency. Current 0.15 amperes, input current amount. Output 5 volt DC. Then we have output current 0.7 amperes maximum current the charger can supply. We have SN serial number R37M87043S4DK3, a unique serial number for identification and tracking. Then we have a production date, April 7, 2009. Then we have a post box, 12987 Dublin, Ireland, the manufacturer or distributor's mailing address, likely Samsung's office in Dublin, Ireland. Then we have made in Vietnam. So, this simply indicates the country of assembly or production. Many original chargers, including those for Samsung and other major brands, are manufactured in Vietnam due to its advanced production facilities. We have CE mark right here, a certification mark indicating compliance with the European Union's health, safety, and environmental protecting standards. We have V symbol, like part of a certification or a voltage indicator. We have here trash bin symbol, indicates the product must be disposed of according to local recycling regulation. We have house with arrow symbol, may indicate suitably for indoor use or represent a return or recycling symbol. We have a QR code right here. The QR code on the charger is typically used for authenticity verification. Can be scanned with a phone to check if it is genuine. Factory traceability helps the manufacturer track production date, production line, and batch or etc. Sometimes links to the manufacturer's website or product support page. Here the QR code directs us to a few websites. Now, let's look at some codes inside the device. What do they mean? At the first, DK11_68. This code likely refers to a mold number or production batch number used during manufacturing. Helps the factory identify the mold or tool used to produce a specific plastic casing. Does not directly indicate material type or electrical characteristic. We have PC here. This refers to the material of the plastic body. PC means polycarbonate. This is a high-quality plastic known for high impact resistance, heat resistance, and electrical insulation. Polycarbonate is commonly used in the casing of electronic devices like chargers because it's strong, heat resistant, and safe for consumer electronics. In conclusion, this charger, as you can see here, is a universal travel adapter designed for 5V 0.7 ampere output suitable for charging low power devices like older Samsung phones, headphones, or accessories, and compatible with various global voltage standards. I've mentally divided this charger into three parts: metal pins, as you can see here, circuit board, and charging cable. Now let's start the main adventure with the first part, metal pins. What are the metal pins and pads? So, the charger's pins are made of copper nickel alloy or brass coated with nickel silver for high conductivity and low corrosion. They are designed as cylindrical pins with rounded ends for easy and safe connection to standard outlets, for example, air plug Type C. The black plastic around the pins right here, as you can see, provides insulation, secures the connections, and protects against dust. The metal strips tabs inside the charger are typically made of copper or brass due to their good conductivity and durability. And as you can see right here. Okay, these strips are designed as thin flat bands and are soldered or riveted to the pin ends to transfer electricity from the pins to the circuit board. So the strips as you can see here, are directly soldered to the PCB surface. And I will show to you right here, as you can see. Okay, no holes as it is an SMD board. The pins and the strips transfer 100 or 240 volt AC electricity to the circuit, which is then converted to the 5 volt DC for charging. Now we've reached the second part, as you can see right here. Yes. Okay, the circuit board, the heart of the device. What do the details on the board tell us? At the first, as you can see here, board production date 13th of June 2017. PCB manufacturer right here, as you can see, Young E.P, likely an electronics component manufacturer. Then we have a charger model here, again repeated, and as you can see, 12R1V and version 2. So these are likely internal codes or technical specification related to the board's version or model. For example, version 2 is noted. 12R could indicate a specific series or resistance, and 1W might refer to watt or another code. These are typically used for internal identification by the manufacturer. Then we have a 1925, as you can see here. This could be a production code, serial number, or part of the boards. A technical specifications. Manufacturers sometimes use numbers to identify product batches or production dates in a code format. So, given the production date right here, this might be part of a production identification code. Letters above that, for example, triangle symbol and letters, this could indicate safety standards or certifications, for example, CE or similar, or factory codes. The triangles typically signifies a warning or specific standard. And right here, #17. This is likely the production line number assembly station or another internal identifier in the factory. So now let's examine the components on the circuit board. What is a fusible resistor? As you can see right here, this is a fusible resistor. Okay, this fusible resistor likely has a 64 kilo-ohm resistance with a 1% tolerance under normal conditions. Its symbol is that and shown right here and is marked as F1. Acts as a protective component on its own. Combines a resistor and fuse. It functions as a resistor under normal conditions, regulating current. If the current exists, the allowed limit typically specified in the datasheet, the fuse blows or opens the circuit, preventing damage to other components. Role on the board. In this charger board, the F1 fusible resistor is located at the AC input near the diode bridge, and its job is to protect sensitive components like the diode bridge, transformer, or capacitors from overcurrent or voltage surges. This ensures that in case of a fault, only the fuse burns out and needs replacement, not the entire board. And now color coding. The colors may also indicate current capacity or specific technical characteristic. But without a precise datasheet, this is an initial value based on the resistor color code. For example, resistor color code standard. For instance, color bands may represent the ohm value, multiplier, and tolerance in sequence. The black base color might indicate the body or insulation. Let's analyze the capacitors, as you can see here and here. Okay, this board includes several Capacitors brand electric capacitors, each with specific roles in stabilizing voltage and filtering noise. Radial electric capacitor, for example, orange, here light blue and dark blue. Aluminum electric capacitor, for example, this white capacitor, as you can see. Okay, and we have a assembly capacitor right back of the board, as you can see right here. Let's see what characteristics each has and why they're replaced on this board. At the first, capacitor 1, here. This large capacitor is on the primary side of the circuit. After the diode bridge converts AC to DC, C1 smooths out residual AC noise and filters the DC voltage. Its 3 microfarad capacity and 400 volts rating indicate its ability to store energy for the transformer. This capacity and voltage are chosen to handle high input voltage, for example 220 volt AC, and provide stable energy for subsequent stages. Then we have here capacitor 2, light blue, also on the primary side with an 85 centigrade operating temperature. And this code is P1922. Its role is similar to C1, filtering noise and stabilizing DC voltage to power the transformer. Its higher 4.7 microfarad capacity compared to C1 helps maintain greater voltage stability under varying load conditions. It complements C1 to ensure a consistent transformer input. Then we have a capacitor C3, as you can see right here. And I will show you this board. Okay. Located at the secondary side designed to stabilize the 5V DC output. Its main task is to filter transformer output fluctuations and reduce electromagnetic interference. Its 202.2 microfarad capacity and 50 volts rating suit the lower output needs of this circuit section, preventing low frequency noise. And now we came to capacitor 4, as you can see right here. Yes. This cylindrical aluminum electronic capacitor with high capacity is on the output side. It filters residual noise and smooths the DC voltage. Its 390 microfarad capacity ensures the charger's output is resilient to sudden load changes and provides stable voltage. Its 7.5 volt working voltage matches the circuit's low output. And the capacitor I analyzed as C4 is marked as C22 on the board, as you can see here. Typically determined by the designer's sequential or logical numbering. This number could relate to the order of capacitor placement, their functional role, for example output filter, or a factory standard, for example PX927 code. Capacitor 5 on the back of the board, as you can see right here. The assembly capacitor on the back of the board acts as an additional filter for high-frequency noise. Due to its small size and surface mount design, it's used in modern circuits to optimize output performance. It complements C4's filtration. So, you might wonder why in the schematic C1 and C2 are shown as a rectangular, as you can see here, and while C3 and C4 are circles. The difference relates to the capacitor type and schematic drawing standards. C1 and C2, these are polar electrolytic capacitors operating at high voltage around 400 volt. So their symbols are designed to indicate orientation, as incorrect connection could damage them. And C3 and C4 located on the output side with lower voltage, 50 volt and 7.5 volt. Their symbols are circular. This could be due to the lower voltage or schematic drawing style, though they are typically polar capacitors in practice. We've reached the inductor, as you can see right here and here. Okay, Specification 7.2 mH with 10% tolerance. Inductor type. The inductor here appears to be a leaded inductor. This type typically consists of a coil with a ferrite or air core, as you can see here, with wire leads designed for board connection. It's likely a single coil inductor, as only one coil is visible. It's typically used to filter differential noise, which is noise that creates a difference between two lines, for example, phase and neutral. The inductor is placed in series with one of the lines to reduce high frequency noise. Ohmic resistance. Inductors are primarily known as inductive elements, and their ohmic resistance is usually low, a few ohms or less, depending on the design and coil material. The exact value requires measurement with a multimeter, but based on its species, this inductor is designed for inductance, not resistance. What is inductance? Inductors are electrical components that store energy in a magnetic field. They're typically made of a coil, often wrapped around a core, and work by resisting change in current due to inductance. What do they do on their own? An inductor limits alternating current by creating inductive reactance, while allowing direct current, DC, to pass with minimal resistance. This makes them ideal for filtering high-frequency noise, for example, electromagnetic interference. Why is an inductor used on board? In this circuit, the inductor combines with capacitors to form part of an EMI filter or switching power supply, for example, power supply circuit, cleaning the output voltage and reducing electromagnetic interference. I think one of the most fascinating and potentially confusing electronic components could be transformers, as you can see here. Yes, you guessed it. We've reached the transformer. The type of this transformer is high-frequency transformer. An application is used in switching power supplies SMPS, particularly in USB wall adapters like this charger model, as you can see here. And let's first analyze the labels on it. At the first, we have DYM628A. So, likely the manufacturer's internal model number. DYM may stand for Dong-Yang Magnetic or Dong-Yang Electronics, matching the Dong-Yang right here, E.P label on the PC. 628A indicates the series or specific model of the component. And right here, as you can see, EP-TA60EBE matches the Samsung charger's model number. Confirms this board is used in an original Samsung charger. And lastly, we have TO1926BHC, likely a production code, batch number, or supplier reference for the core or coil style of the transformer. May be used to track production data or specific design variations. Now, what's the transformer's role? In the charger, it converts high AC voltage from the input after rectification into a low pulsed DC voltage to provide the device's required energy. Then provides electrical isolation between the high voltage input and the USB output, ensuring device safety. Works with a switching transistor, usually nearby, and a control IC to regulate voltage and current. Why is it mounted on black piece, as you can see here, here, and right here? Okay, because this base, typically made of resin or insulating plastic, provides mechanical stability, offers insulation, and is heat resistant, also acts as a barrier between high and low voltage sections. Topologically, it's likely a flyback type common in low power chargers and works with a switching IC. Now we came to the structure and pins. Contains multiple coils, secondary and primary, and a ferrite core for efficient energy transfer. The primary side has 5 pins including the main coil and sometimes an auxiliary coil for feedback or IC power supply. Extra pins may be used for spacing, protection or voltage regulation, and the secondary side has 2 pins with a simple output coil for low voltage, for example 5 volt. Now for the connection details based on the flyback design. Let's look at the transformers pins. Right here, primary pins. There are one on the input side of the circuit. One pin connects to DC bus. After AC power passes through the diode bridge and capacitor, it becomes DC and enters this pin. The second pin connects to the transistor collector in our circuit with the OB25133 IC. This pin connects to the internal switch transistor pin in the IC. In other words, when the IC turns on, its internal switch current flows through DC bus to transformer, then transistor and ground. This stores energy in the transformer's core. And auxiliary pins. These pins serve two purposes: supplying VDD voltage to the IC via a diode or internal path and providing feedback for output voltage for voltage control. Typically, one auxiliary pin connects to feedback resistor, for example right here, circuit, and goes to the IC's FB feedback pin. There may be a diode between the auxiliary pin and VDD as the transformers release energy powers the IC self-supply. Now we came to the secondary pins. These pins transfer energy to the charger's output section. One pin connects to the anode of the output Schottky diode right here, as you can see, and which allows electricity to flow from the transformer and to the output only when energy is realized. And the other pin connects to the output ground, for example the negative terminal of the filter capacitor and the negative pin of the charger's output connector where the USB cable connects. When the transistor turns off, the transfer through secondary coil to diode, filter capacitor, and then output. Now we came to the resistors, as you can here, right here, and here. Resistors are fundamental components in electronic circuits with the primary role of regulating current and voltage. In this board, SMD surface mount device resistors are used, soldered as tiny components onto the board surface. Main roles of resistor in this circuit are dividing voltage to create a reference or feedback for ICs, limiting current in the input or output paths, current sensing for control and protection, serving as test points for measuring voltage or current during. So, factory tests or repairs. Let's examine the resistor on the board. At the first, we have RS1 right here, as you can see. So, 2 ohm test point for measuring output voltage or current sensing resistor. R1 and R2 right here, 2.2 mega ohm voltage division and providing feedback to the IC. R3, as you can see here, 1.5 mega ohm controlling output voltage or feedback. R4 and R5, as you can see here, R4 is 154 ohm and R5 is 18 kilo ohm. Feedback or current sensing for the switching IC. We have R7 resistor here and 2.4 ohm. And lastly, we have R8 and R9. R8 is 10 ohm input current sensing and R9 unspecified, likely complements the current sensing resistor. For summary, on this board, resistors do more than just reduce voltage or current. They play critical roles in feedback or for switching circuits, output control, circuit protection, and current monitoring. Each resistor with its specific value has a process function in the circuit design. Now we came to diodes. As you can see here, we have diodes and here D5 and D6. This charger board uses two SMD diodes for rectification and protection. D5, likely type Schottky diode or fast recovery diode. The role: fast rectification at the switching converts output, reducing voltage drop and managing inductive current from the coil. And position behind the transformer, it's likely rectifiers that transformers secondary output and prevents current backflow. Now we came to D6 SS25. Model of that is Schottky diode and is 2.5 ampere. The role of this diode is protection against ESD and reverse voltage. Act as a freewheeling diode to protect transistors. Position behind the transformer, it's likely serve as a clamping diode, neutralizing inductive voltage spikes and protecting transistor or controller ICs from damage. Note: Schottky diodes with their low voltage drop, for example 0.2 to 0.4 volt, improves circuit efficiency. Voltage clamping. A diode or a combination with resistor capacitor limits voltage to a specific level, directing excess voltage to ground or a safe path, especially to protect against inductive spikes from the transformer or switch. The position of D5 and D6 behind the transformer indicates their role in managing inductive voltage generated in switching converters when the primary coil current is cut off. So now we came to the OB25133 IC. It is one of the key components on this board. Let's see what it is and what it does. The OB25133 IC is an AC-DC switching controller with primary side regulation (PSR) technology. It doesn't convert voltage on its own, but preciously controls the switching process in switching power supply circuits, such as mobile phone chargers. Main task in the circuit: at the first, generates PWM pulse width modulation pulses to turn the power transistor on and off. Preciously controls energy input to the transformer for voltage conversion. Regulates output voltage using feedback through the FB pin without needing an optocoupler. Senses primary current through the CS pin to prevent overclock. Supplies its own power through the transformer's auxiliary winding and enables energy saving mode, burst mode, during no load conditions. Provides protection against conditions like over temperature and under voltage lockout. According to the datasheet, the IC pins function as follows. Okay, at the first we have VDD pin, IC power supply. Main role is power the IC. How does it get power? As you can see here, yes. At startup, when the IC isn't yet active, a resistor from the DC bus called the startup resistor trickle charges the VDD capacitor. Once the voltage reaches a sufficient level, the IC turns on. After that, the IC's power no longer comes from this resistor, but from the transformer's auxiliary winding. But AUX. AUX stands for auxiliary, meaning helper. This winding acts like an internal charger supplying the IC's required voltage from the transformer. Then we have a FB pin, feedback. Main role: preciously regulates output voltage without an optocoupler. How does it work? The auxiliary winding AUX is active only when the output voltage is stable, so its voltage is a good indicator of the output status. The FB pin receives a scaled down voltage, for example 2.5 volt, from the auxiliary winding via a voltage divider resistor. The IC uses this voltage to decide whether to increase or decrease the output. This method allows the IC to control the output with an optocoupler. Then we have NC, no connected pin. This pin isn't connected internally in the IC. It's used only for physical form or board stability. Then we have CS pin, current sense. The role is overcurrent protection. How does it work? A very small resistor, for example 0.5 ohm, is placed between the negative DC supply and the IC's ground. When the current flows through the transformer, it creates a voltage drop across the resistor. This voltage goes to the CSP. If it exists a certain threshold, the IC immediately turns off the internal switch transistor to prevent circuit damage. Then we have 5 and 6 pins. Collector of the internal power transistor. The IC has an internal power transistor and these pins are its collectors. How are they connected? They connected to one end of the transformer's primary coil. When the transistor turns on, current flows from the collector, C pin, to the emitter, Ganede pin, right here. This switching inducts energy in the transformer. And lastly, we have G and D pin, circuit ground. This pin is the emitter of the transistor and the IC's voltage reference. All negative voltage, for example, output negative and auxiliary winding negative and C as resistor negative, connects to this pin. In summary, the OB25133 IC sends the primary coil's current strength through the CS pin and reads the output voltage via the FB pin. Right here, auxiliary winding. Switching is performed by current flowing from the C pin's collector to the G and D pin emitter, and the VDD startup circuit includes a large resistor, and after initial startup, the transformer's auxiliary winding provides stable voltage to the IC. So, what is B1? As you can see here. Okay. On printed circuit boards, the label B1 typically isn't an abbreviation for something specific, but it can have different meanings depending on its position and shape. In this board, as you can see, B1 is located near a bridge rectifier labeled BD1. This component is a small black SMD part that looks like a resistor, but lacks the typical resistor markings. So let's explore what B1 could be. At the first, it can be resistor, voltage protector. If near the IC input, it's likely designed to protect agents' voltage surges. Then it can be NTC thermistor. If in series with the AC input, it limits in rush current when the device is powered on. It can be resistible fuse, PPTC. If in the power pad or near the input, it could be resistable thermal fuse that protect against overcurrent and resets after the fault is cleared. And also it can be ferrite bead, as you can see here. If in the power or signal pad, it's used to filter high frequency noise. So, given B1's position next to the BD1, it's more likely a ferrite bead or NTC thermistor. These are commonly used to protect the power line or suppress EMI noise. Since it resembles a resistor but lacks marking, it's unlikely to be a resistor. However, based on its position, a resistible fuse is also a plausible option, especially if the circuit designer prefers overcurrent protection. So for summary, we conclude with that B1 is likely one of these three components: a ferrite bead of noise suppression, an NTC thermistor for inrush current limiting, or a resistible fuse for overcurrent protection. If you see a similar component on your board, now you know what it might be. And now we came to the ABS10D. And here, as you can see, The component labeled ABS10BD1 on the charger board is a bridge rectifier diode. The model is ABS10. It converts AC input to DC and serves as the first stage in the charging process. It's typically in an SMA or SMB package and supports a nominal reverse voltage of 1000 volt and a nominal current of 1 amp. The D is A in ABS10D is likely manufacturer suffix, for example for packaging or protection code, and doesn't affect electrical performance after the AC passes to the fuse and filter. It produces an approximate 320 volts DC peak input voltage. Back of the board, the two squares, as you can see, areas at the bottom of the board are where metal pads are soldered, transferring current to the device. We have golden slots. These slots are used to align pin spacing during automated assembly, helping the manufacturer place components preciously. And solder joints, as you can see. These sliver points securely connect components to the board. If done well, the charger will work for years. The metal lines right here and here you see are electrical tracks that carry current from one part to another. For example, tracks near the pads carry current to the output, while those near components like capacitors and resistors regulate current. This design ensures the charger functions smoothly and everything is interconnected. Yes, we've reached the third section, as you can see here. Okay. The cable and its components. At the first, we have 2-pin connector or 2-pin buffer, shown here with this symbol, as you can see right here. Okay, so what is that? This small component, typically with 2 pins, is used to connect cables to printed circuit boards, PCB, such as in chargers, electrical toys, or simple devices. This connector helps transfer current safely and easily. One of the most common is the GSTPH, widely used in die projects and repairs. Installation is straightforward. Just solder the pins to design points on the board. Now let's check the back of the board, and I will show it to you right here. We need to ensure the soldering is strong and the connection is solid. So, in this section, we have a black USB cable that is non-detachably connected to the adapter. This means the cable is permanent part of the adapter and typically connects to a micro USB socket on the other end. So, internal structure of the cable. At the first, we have outer sheet, a PVC or flexible plastic coating for mechanical protecting of the internal wires, shielding and aluminum foil. Layers that reduce electromagnetic interference EMI, enhancing the cable's performance, stability, internal wire stability. And we have internal wires. Unlike standard USB cables with 4 wires, this cable has only 2 internal wires. White wire for carries positive current and black wire G and D serve as ground or negative. This cable is designed solely for charging devices and does not support data transfer. Installation for each wire. So each wire is covered with a thin insulating layer to prevent short circuits and reinforcement gun or heat glove, typically found at the cable's connection to the adapter or connector to prevent tearing or damage. Important note, due to the fixed and interacted design of these cables, if the cable is damaged, the entire adapter must be replaced, as the cable is not detachable. For summary, the simple fixed cables are commonly found in older or budget chargers, focusing solely on stable power transfer without the need for data exchange with computers or other devices. Now let's look at the internal structure of the connector part right here. As you can see, what is it made of and what does it do here? This part, as you can see, of the USB cable plays a critical role in transferring power and data between the charger and the phone, consisting of various components. At the first, we have metal pins. Here you see 5 metal pins in the USB connector. For example, a micro USB or USB-C. Each pin has a specific role. At the first, we have power pin VBUS. Transfers 5 volt power from the charger to the phone. Ground pin G and D provides the return path for current the insurance circuit. Then we have safety. Then we have data transfer pins D positive and D negative, used for data transfer between devices such as when connecting a phone to a computer. And lastly, we have identification pin CC or ID. In USB-C, this pin identifies the connector's orientation and manage power. These pins are made of materials like copper or corrosion resistant alloys for good electrical conductivity. Then we have a metal layer right here, as you can see. The metal part surrounding the pins is likely made of aluminum or a lightweight alloy. This metal layer, light and durable. Aluminum is ideal due to its low weight and good durability, protecting pins from pressure and impact. Electrical conductivity may also act as shielding to reduce electrical noise. It has two main purposes. At the first, holding pins in place keeps the pins securely in position, and secondly, preventing short circuits separates pins to avoid unwanted contact and circuit failure. Then we have a white lower part, as you can see here. Okay, the white part beneath the metal layer is likely made of insulating plastic, such as polycarbonate. This section has 2 roles. At the first, separating wires keeps the current carrying wires black and wires apart to prevent short circuits, and secondly, connecting 2 pins acts as a base soldering or connecting wires to the metal pins to transfer current and data to the device. And lastly, we have outer covering, as you can see here. This outer protective layer is typically made of durable plastic or lightweight metal like aluminum. This covering has 2 roles. At the first, physical protection protects wires and pins from impact, moisture, and dust. And secondly, secure connections. First, fits snugly into the phone's socket to maintain stable electrical current. From a scientific perspective, a supplementary explanation. Okay, from an engineering standpoint, this connector must comply with electrical standards like USB 2 or USB-C. Low electrical resistance, temperature tolerance, and cable flexibility are key design considerations. So, the external charger operation looks like this. It uses a 2-pin metal plug to connect to mains electricity, AC, and has a USB-A output port that delivers DC power to the cable and ultimately to the phone or device right here. Now let's dive into the internal operation and circuit components. In brief, inside the charger, inside the charger, at the first we have electricity enters through the pins, then passes through fuse, then reaches the bridge rectifier. We have capacitor smooths the voltage, goes to USB, output is filtered, and transformer steps down the voltage. So, but in the tile we have these steps. Yes, you can see it now. At the first step, AC input and protective fuse. The input alternating current, 220 volt or 110 volt AC, enters the board through metal pins right here via a fuse or fusible resistor, FP, typically a few ohms, as you can see here. This fuse is the first line of defense, protecting the circuit from short circuits or excessive input current. Often, an electromagnetic interference filter is present at this stage to prevent noise and sudden voltage spikes from entering the circuit. The second step, voltage rectification. Bridge rectifiers, right here. After the fuse, a bridge rectifier BD1 with 4 rectifier diodes converts the input alternating current AC to direct current DC. Simple put, the bridge rectifier uses diodes to allow current flow in one direction, converting AC to DC. The result is an unfiltered DC voltage which, after passing through the large input capacitor C1 right here, reached approximately 310 volt DC. Capacitor C1 smooths this DC voltage, reducing excess ripples and providing stable internal voltage. So, the third step, internal switching and playback transformer. In this circuit, after the AC is converted to DC and a high voltage of about 300 volt is optioned, this voltage enters the OB25133 control IC. This IC has an internal power transistor that switches on and off rapidly, enabling energy storage and transfer in the flyback transformer. When the IC's internal switch is on, energy is stored in the transformer's primary coil. When it's off, this energy is transferred to the secondary coil and converted to a lower voltage. So, thus the entire switching and voltage conversion process is handled by this IC, as you can see here alone, without needing an external transistor. In the flyback architecture, the transformer predictably stores energy in its core and then transfer it to the output. So when we have a switch on right here, as you can see, energy is stored in the primary coil. When the switch is off, stored energy is released to the secondary coil and producing the output voltage. Now we came to the fourth step, output rectification and filtering. The transformer's secondary voltage, about 5 volt AC, is first rectified by a fast diode or Schottky diode right here into direct current DC. Then an LC filter, inductor L1 and capacitor C2, C3 and C4 removes high frequency noise and ripples, stabilizing the output voltage. Many circuits use Schottky diodes with short recovery times to reduce switching losses. Capacitors store excess energy when the switch is on and deliver it to the load when the switch is off, keeping the 5 volt output voltage stable. The fifth step, feedback and output voltage regulation. The OB25133 control IC monitors the output voltage and load current, adjusting the pulse width, the duration of the switch on time to off time. This feedback is typically provided through a resistor divider circuit, R1 or and R5 or an optocoupler, maintaining electrical isolation between the primary and secondary circuits. When the output voltage slightly rises or falls, this information is sent to the IC via the optocoupler. The IC then adjusts the internal switch on time to establish the output voltage back at 5 volt. And lastly, we have output protection. At the USB output pad, a reseatable fuse, B1, or overcurrent protection circuits and a protection diode, right here, D6 or similar, are typically used to prevent circuit damage in case of a short circuit or reverse voltage from the battery to the charger. These safety measures extend the charger's lifespan under abnormal conditions. So for overall, the printed circuit of this charger is a standard playback switching power supply utilizing common SMPS design components, a rectifier bridge diode, filtering capacitors, an isolation transformer, a PWM switching transistor, and an output LC filter. Designed to operate in the global voltage range 100 to 240 volt AC, the switching method, unlike all the linear regulators, which reduces energy loss and allows smaller transformers and components, and precious control approximately 0.7 ampere current. So this isn't just a charger. It is a precise and smart piece of engineering that uses switching technology to transfer energy from the wall to our digital lives. Behind the simple appearance of this small charger lies a complex world of engineering, where all components work together to ensure our device is charged safely and correctly. Don't forget to like, comment, and subscribe because we are going to keep progressing together. Until the next part, bye!